whether you can see the PowerPoint? Any one of you?
Yes, ma'am.
Okay, good. Fine. We can start the class. We'll see the strength. Around 33 people. 48 is the strength of the class. There should be 49 in the chat box, in the people, the participants. It is going on increasing. Anyway, we'll see for just, we can see for 2-3 minutes and we will start the class. See, at the end of the class, before you leave the room, you have to tell your, according to your roll number, you have to tell that present. I will call out your name and you have to unmute your mic and you have to tell your attendance. Okay. Anyway, this will be at the end of the class. Now, the time is, what is the time right now? 10 o'clock. We'll wait for 2-3 minutes and we will start this. We'll see. I think we can start the class right now. $59. Now, shall I start the class? Whether my audio and video is audible to you? Anyone? Unmute.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, you unmute and I'm going to start the class. Okay. Now we have seen laser, light amplification by stimulated emission of radiation in the previous 2-3 classes. See, this laser application, one of the application of laser, after invention of laser, one of the main application is optical communication system. Fiber optic communication system is the one of the main application of that laser. Laser, you know, it is used for welding, cutting, drilling, etc. That is engineering application. Then apart from that, in engineering application, in communication system, this fiber optic, after laser invention, this optical fiber, this is invented. We will see in detail. After optical fiber is invented, then using laser, the communication system, that is you are transferring the audio, video, digital signals over a long distance using light wave. That fiber optic communication have become and that technology have come into action, and it is a till now it is a successful technology, optical fiber communication. Anyway, regarding that, we are going to see in detail the fiber optic communication, fiber optics. About fiber optics, we are going to see the basic thing, basic concepts, how this fiber optic cable is constructed. Now, what is this? Like that, we are going to see. Now, see, we know optical fiber means it is invented after it is used only after the invention of laser. Okay. Now, where this optical fiber is the how it is developed, how it is used, from the basic we are going to see. See, this is the optical fiber cable. This is outer inside the outer jacket, black polyurethane outer jacket. Lot of fiber optic cables are there. That glass needle in that diagram, in this picture, that glass needle, optical fiber. First, you have to know how it is. It is nothing but a glass needle. Optical fiber is nothing but a glass needle. You know that glass needle, you know how it is, how needle is. Needle is a solid cylinder. It is not a hollow cylinder. Like that, optical fiber is also a solid cylinder. It is a glass, a solid cylinder made up of glass. It is a kannadi oosi. In Tamil, we can say it is like a kannadi oosi. That is glass needle. It is a solid cylinder. It is not hollow. Hollow cylinder. It is not having any hole or opening at the center. It is a solid cylinder. And how much is its thickness of this glass needle? Means its thickness is of a few micrometer. That is 50 to 100 micrometer is the diameter of that glass needle. What is 50 to 100 micrometer means? How much will be the dimension? For that also, to imagine, I will also give you another clue. See, the hair thickness, the thickness of a hair, human hair, is 10 micrometer. If the thickness of the human hair is 10 micrometer, then this glass needle thickness is of around 50 micrometer to maximum 200 micrometer. Then means 50 micrometer means 5 hair thickness. Take 5 hair and join together. How much thickness it will be? That is 50 micrometer. So the optical fiber, this glass needle, is of order of 50 micrometer to 200 micrometer. 200 micrometer means it is of order of thickness of 20 hair. 20 hair, human hair together. If you make a bundle, how much will be the thickness? That is 200 micrometer. For your imagination, I am telling. So this optical fiber is a glass needle, glass, CiO2, silica. It is made up of silicon dioxide, silica, glass needle. That is, and its thickness is of order of 50 to 200 micrometer approximately. In that thickness of a glass needle means it is a solid cylinder. Inside that cylinder, glass needle, the light wave, which is an electromagnetic wave, mainly which is a laser light, will be allowed to propagate through the glass needle overall thousands of kilometers by the principle called total internal reflection and reach the exit end of the glass needle. This glass needle it may be of several kilometer thickness. We can construct this glass needle. We cannot prepare a glass needle of for 300 kilometers. Joining couples will be there for every 20 kilometer or 10 kilometer. There will be a coupling unit to join this glass needle, which is a separate technique called splicing. So we will join this glass needle fiber over. This is for your imagination. Before starting, what is optical fiber communication? I am giving you just an imagination how this optical fiber cable will be. So this through this glass needle only, the light wave, that is mainly the laser light, is allowed to pass through the glass needle within that small diameter, 50 to 200 micrometer diameter, and it is by the principle of total internal reflection and reach the exit end. The exit end of that optical fiber will be after 3000 kilometers. So this optical wave, light wave, is not just like that passing through the glass needle like a water flowing through a rubber tube. It is not just like that traveling. It is carrying, it is acting as a carrier wave, carrying the information signal. The information signal may be your audio signal, that is telephone, or video signal, TV reception, or some digital data from one computer to another computer, data bytes will be transferred through the light wave as a carrier wave in a what? Somebody should unmute. Sorry, mute your mic. Somebody is making a sound. So through the glass needle, this light wave, which is going to act as a carrier wave and is carrying the information signal and reaching the exit end. So across this optical fiber at the transmitting end and receiving end, there will be a modulator and demodulator, so that the information signal is retrieved at the receiving end. That is a separate process. Just for a sketch, just to give an idea what is optical fiber, what we are going to study for next 2-3 days. Just an information, just the thing. This glass needle made up of this needle made up of glass, which is a solid cylinder, which is used for communication system. About that, all the basic concepts, how the light is entering and act as a carrier wave to carry the information signal. All these basic things we are going to study. All these things. What is the basic physics involved in this transmission of light wave to carry the information signal? All these things we are going to see how it is constructed, how it is, how this idea came, what are the demos, laws govern them to construct this optical fiber. All these things we are going to see today. Okay. Now, see this optical fiber construction. How this idea, through the glass needle, we can use light wave as a carrier wave and carry the information signal over a longer distance. How this idea came and how this optical fiber is constructed, that comes how it originates is, the basic thing is Tyndall effect. In 1817, John Tyndall introduced a concept of total internal reflection with a demonstration. This Tyndall effect only is responsible for the propagation of light through the very thin cylindrical optical fiber. So Tyndall, that we are going to see today. Okay, this Tyndall effect. Next, in the same year, in the 1817, Alexander Graham Bell developed an optical voice transmission, which he named photon. So these things are the main photophone. These are the main telephone, the photophone. These things are making this Tyndall effect, and we can send a light wave for voice communication. Demonstration in the same year by Alexander Graham Bell only is the basic foundation for the optical fiber communication. Okay, now see, before that, this optical fiber communication is there. There is only a what before that, what the same Alexander Graham Bell have, this audio telephone conversation, telephone communication is through the what copper cable as the channel. Electrical wave is the carrier wave through the copper conducting wire to pass through. That will, electrical wave will carry the audio signal. That is the conventional telephone communication system, which Alexander Graham Bell have constructed first. Instead of this optical fiber glass needle, you are using a copper wire. That is the pathway, channel, or waveguide. I will tell you waveguide. What do you mean by waveguide? Waveguide, that is a tubular structure where any sort of electromagnetic wave will transmit from one end to another end by with the minimum loss. That is called a waveguide. You note this information. Waveguide. What is waveguide? Waveguide is a tubular structure. Waveguide is a tubular structure where any sort of electromagnetic waves, can be transmitted from one end to its other end with minimum loss. See, the tubular structure, the electromagnetic wave may be any type. You know what are the different types of electromagnetic wave? Radio wave is there, microwave is there, electrical wave is there, light wave is there. So any sort of electromagnetic wave have to travel from one end to another end. You need a pathway, you need a channel. Like for example, you are having a water filled in a tank. Now that water you have to irrigate to the plant, or you have to bring down the water for any domestic appliance, sorry, domestic uses or something. If you want to bring the water which is filled in the tank for watering the plant or any for any domestic purpose, what you have to use a pipeline. So through the pipeline, that pipe, the steel pipe or a rubber tube or rubber, any pipe made up of any material is the pathway or a channel through which this water is transmitting from the tank to the receiving end, maybe a garden or a domestic use, any purpose. Okay. So like that, the electromagnetic wave is going, it is a very high frequency waves. These electromagnetic waves is going to act as a carrier wave to carry the information signal. The information signal may be an audio signal or a video signal for television broadcasting purpose, or any digital data. Any information signal should carried from one end to the another end. The distance between the transmitting end and the receiving end may be several 10 kilometers or 1 kilometer or 1 meter from one computer to another computer, or several thousand kilometer ISD, international call. So if the information signal has to be transmitted from one end to another end, that is transmitting end to the receiving end, however the distance vary, this information signals like audio signal, video signal, digital signals, they are all less frequency, less energetic wave. They cannot be simply just like that transmitted, because if I speak, it can be transmitted only if I talk in a classroom. It can be heard to the students inside the classroom, just a few meters outside the classroom. But when I am speaking, if my audio signal should be transmitted over a thousands of kilometers wherever you are, then that my information signal, my audio signal should be transmitted over a through a energetic wave. This energetic wave is called a carrier wave. These waves are mostly electromagnetic waves. So the electromagnetic waves may be a radio wave or a microwave or an optical wave. So these etc. There are a lot of electromagnetic waves. So you know there are different type of electromagnetic waves. So all these electromagnetic waves cannot pass through same channel, same pathway. If electrical wave is a carrier wave to carry the information signal, the channel used, the pathway used, the waveguide, the tubular structure used is a copper conducting wire. So this is the first telephone communication system. The copper conducting wire, copper cable is used as a channel or a pathway for transmitting the electrical wave, transmitting the audio or a video or a digital wave, digital data from transmitting end to the receiving end, with the electrical wave as a carrier wave. Electrical wave will be acting as a carrier wave. That is the electromagnetic wave, which is going to act as a carrier wave. Now, when a current passes through a copper wire, it will produce a magnetic wave. So, the electrical wave is an electromagnetic wave, which is passing through the copper cable. This is going to act as a carrier wave to carry the information signal. This, how it will carry means, that is a separate technique. At the transmitting end, you will modulate. Modulate means you will superimpose the information signal, audio or video or a digital signal, with the carrier wave, the resultant wave is called that is, you are superimposing with the electromagnetic wave, so that the resultant wave is called the carrier wave. The carrier wave will pass through the through the proper channel pathway. So the carrier wave has the is nothing but an electromagnetic wave which have the impression of the information signal. So that carrier wave through the copper cable, if it is an electrical wave, is a carrier wave which have an impression of the audio or a video or a digital signal, will act as a carrier wave and pass through the copper cable and reach the receiving end. Receiving end demodulate the carrier. In the carrier wave, the electrical wave is there, the information wave is there. So they are separated. Their frequency, depending on the frequency range, they are separated in a filter circuit. Then this audio wave alone, they get they will be after proper amplification. It will be retrieved through a proper circuit. That is, if it is an audio signal, the electrical wave corresponding to the audio signal is fed to the loudspeaker and you will get the sound signal. If it is a video wave, the electrical wave corresponding to the video signal is fed to the picture tube and you will display the video signal on the television screen. So like that. That is a separate demodulation technique. So what I have to tell you here is the optical fiber is a waveguide. It is a tubular structure where any sort of electromagnetic waves can be transmitted from the transmitting end to the receiving end with a minimum loss. Here, optical fiber is a waveguide made up of silica or a glass fiber of 50 to 200 micrometer diameter, which will transmit the light wave as a carrier wave to transmit, so that by the principle of light wave as a carrier wave, by the principle of total internal reflection to reach the exit end. That we will see in detail. So I will tell you this again in detail. Now, how the light wave through the thin cylindrical optical fiber is transmitted and reach the exit end is how it enter through this thin cylindrical glass fiber of 50 to 200 micrometer. I have told you how will be the thickness. It is a 5 hair thickness or to 20 hair thickness. That much thin glass, within that thin glass needle, how the light is entering. That how that is possible is the first demonstration is done in the year 1817 by Tyndal. That the concept introduced is by the principle of total internal reflection. Now, later, see, after total internal reflection, by the principle of total internal reflection, the light can propagate through a medium without any loss. That is demonstrated in the year 1817 by John Tyndall. Next, Alexander Graham Bell also demonstrated that light can be used for transmitting voice communication from one end to another end in the very same year. These both the thing happened in the year 1870. Next, in 1954, Brain, Hopkins, and Kapani achieved a low loss transmission through 75 centimeter bundle of 1000 fibers. 1000 glass fibers they took, and its length is of order of 75 centimeter. That through that bundle of 1000 fibers, with a minimum loss, the light wave can be propagated. That they have demonstrated in the year 1954. Then John H. Mizizawa was the first to propose the use of optical fibers for communication in the year 1963. They are all proposing. Okay, it is proposed. It is not implemented. Now, Kongu and Hoffman were the first to reduce attenuation loss. So, when a light is passing through the glass needle, there is a loss of light energy, light signal, which is coming at the exit end, that is receiving end. So, that loss should be, if the more loss is there, then what happened? The light reaching the exit end will be very less. The light is not alone, the light is coming. It is carrying the information signal. So if light energy coming through the optical glass needle, if there is a loss, the information signal which it is carrying is also will be lost. So we have to minimize the loss of the light energy when it is passing through the glass needle. So that attenuation loss is reduced to about 20 decibel per kilometer. This is for this is after in the year 2009. This 20 decibel per kilometer only, when 1 kilometer if the light signal travel, only just 20 decibel of light energy is lost. That much minimum loss is come into effect, then immediately the fiber optic communication is a very good, efficient, effective communication. So for that demonstration, which was done in the year 2009 by Cavo and Hockham, this Cavo have earned a Nobel Prize for it. This is a notable one for you. This is an information for you. Now, okay, this is the history how the optical fiber is what actually Corning laboratory. These award from that actually two workers have constructed this optical fiber. That I will, after that I will tell you. These are all the history how the optical fiber we can, who constructed the first optical fiber. All these things they are working in a Corning glasswork company, and all these things I will tell you later. Now, okay, now we will go back again. What is Tyndall effect? Because this is the basic concept demonstrated by John Tyndall in the year 1870, which have later in the year 1960, have 1957. This fiber optic communication has 19 what 60, after the laser invented. This fiber optic communication has come after that 1960. After that only, after laser have invented, this fiber optic communication have come into effect. Okay, now so this John Tyndall in the 1870, what he told, that is the basic concept for the propagation of light through the thin glass fiber by the principle of total internal reflection. So what is this Tyndall effect? We are going to see. This is just a basic thing. Now, what the Tyndall effect actually, what does it mean? Means when a light is passing through a medium. Okay, the medium should have some particles. The particles should have a sufficient size so that when a light passes through the medium, it is scattered by the particles. Because of that, the path of the light through the medium is visible. This is actually the Tyndall effect. Suppose when a light is passing through the medium, if the particle size in that medium is not sufficient for the light wave to scatter, even though the light is passing through the medium, you cannot visible the light which is passing through the medium unless the particle size is a particular range that we are going to see. This is the actual thing about the Tyndall effect. So what is Tyndall effect is the visible path produced by a beam of light passing through a colloidal mixer caused by the scattering of light by the dispersed particle. This thing only, this Tyndall effect is actually telling you. See, here in this picture, a light is passed through the two beaker of solution. Two beaker, some liquid is there. One is solution and another is a colloid. The solution means in that the solvent and the solute, that the particle size of the solute will be of very fine, very small size. So the solute and the solvent will dissolve completely, and there will be no particles. The particles are completely dissolved. So the that is called a solution. So in a solution, excuse me, in the solution there is no chance for the presence of particles of finite size. So when even a light pass through the solution, because the particle size is not that much larger for the light wave to scatter, you cannot see the path of the light wave through the solution in the first beaker. But in the second beaker, it is having a colloidal salt. Colloidal salt, it is a liquid in which the through the solvent some solute is dissolved, and the particle size of the solute is such that it is a very larger, so that it is not dispersed completely, just it is dispersed throughout the solution solvent. So when a light wave passes through that colloid, what happen means the particles in the colloid will make the light wave to scatter. As a result, the path of the light wave through the water through the colloid will be visible in the second beaker. So this is actually the Tyndall effect. So you need a particle of definite size for the light wave passing through it to scatter, so that the path of the light wave will be visible. Okay. This is a beaker of some liquid is placed. One is in the form of a solution and another is in the form of a colloid. This may be applicable for gas also. This may be applicable for a solid also. The part it is not only applicable for water liquid. This can be applicable for gaseous region also and solid also. See here, you're in that when there is a sunset, you are seeing a red color. Why are some sunsets are red? The atmosphere contains, so this Tyndall effect can exhibit in first we have seen in the colloid and solution, this Tyndall effect. It can be seen in the gaseous state also, in the space. Air particles are there, air is there, it is having air particles. If the air particles is of a reasonable size, the light coming from the sun will be scattered by the air particles present in the atmosphere. So that in the atmosphere, not only air particles, there will be a in the which is in the gaseous form, there will be a water particles, will be a dust particles, which is a solid. So the atmosphere contains particles of water and dust. As sunlight passes through the particles, it is gets scattered. However, not all wavelengths are scattered, so the red is mostly scattered, so it appears hot red. That is the one reason for this thing. This I will tell you again in detail. So this appearing of sky in the form of red is due to the Tyndall effect. See, light scattering phenomena. This how the sky gets scattered during this sunset. This is another diagram for this is a Tyndall effect. So what is Tyndall effect? So the scattering of light by the particles in a medium. The medium may be a solid, liquid, or a gas. But the Tyndall effect, mainly in the laboratory, they are demonstrating with the liquid only. Now, so this how the Tyndall effect takes place. For Tyndall effect to takes place, the medium has a particle of definite range. For that only, this suspension, solution, all this example we are going to see. What is suspension, solution, and colloid? Where this suspension in a suspension, solution, and colloid all are in a liquid form. The particle size in it only will vary. Now we will see what is suspension. A suspension, we are going to see what is suspension, solution, and colloid. Now, a suspension is a mixer from which particles settle out upon standing. See, we are taking a solvent and a solute and dissolve it. While dissolving, after some time, the particles of the solute is settled down. Then it is called a suspension. A suspension differs from the solution because the particles of a suspension are much larger and they do not stay suspended indefinitely. But in the case of a solution, what happens means When a solute and the solvent is dissolved, the particles of the solute completely dissolve. There is no settling down of the particles. So, in a solution, what happens means the particle size is very fine. So, it is completely dissolved in the solvent, and there is no settling down of the particles. So, suspension, the particle size is larger. So it will settle down. In a solution, the particle size which is dissolved with the solvent is of what? Very small. So it is completely dissolved. So we can't. It is a very. It is having a very fine particle size. So you cannot. The particle size in a solution is not. Uh, it is negligible. It is very small. Now the particles in a suspension have an average diameter greater than 1000 nanometer. Nanometer means 10 to the power of minus 9 meter. See, micrometer is itself 10 micrometer means 1 hair thickness. That is 10 power minus 6 meter. Nanometer means 10 power minus 9 meter. That means what? It is very smaller than hair thickness. So the diameter, the particles in a typical suspension have an average diameter greater than 100 nanometer. But by contrast, the particle size in a solution is still more less. That is about 1 nanometer. A solution is a homogeneous mixture. That is the uniformly mixed. The particle is completely dissolved with the solvent. So it is thoroughly mixed, uniform density. It is mixed throughout the solvent. Suspensions are heterogeneous because at least two substances can be mm, distinguished. So it won't mix uniformly. That is heterogeneous. So solution has a particle size of 1 nanometer. Suspension, the particle size are huge, so that the particles, when it is dissolved with the solvent, it will settle down, precipitated down. Because the particle size is of order of 1000 nanometer, then another type of liquid is there, that is colloid, that we will see. Before that, I have to tell you the difference between the wait. A suspension is a mixture from which particles settle upon standing. Again, I will tell you, a suspension differs from a solution because the particles of a suspension are much larger and do not stay suspended indefinitely. The particles in a typical suspension have an average diameter greater than 1000 nanometer. By contrast, the particle size in a solution is usually about 1 nanometer. A solution is a homogeneous mixture. Suspensions are heterogeneous because at least two substances can be clearly identified. We can clearly identify the solvent particle and solute particle. Then the difference between the solution and the suspension is easily seen. See, in the first picture, the solute particle in a solution allows them to pass through the filter paper. You are taking a suspension, and with the help of a filter paper, you are filtering the small size of the solute particle in the solution. The first is a solution. The second picture is the suspension. Because in the solution, the particle size is very small of 1 nanometer, and it is homogeneously uniformly dissolved with the solvent. When you pour a solution in the first picture through the filter paper, the particle size is so small that particle also filter into it. So the same solution is inside the beaker. But in the second case, the suspension, because the particle size is very large of 1000 nanometer, this is 1 nanometer, here 1000 nanometer, then it is, so when a suspension is filtered through a filter paper, what happens? The particle size of the suspension is so large, it is filtered by the filter paper, and only the solvent is coming to the beaker. This experiment proves that suspension, the particle size is very larger. In a solution, the particle size is very small. Another example, A mixture of sand and water can be separated by filtration, but cannot a mixture of salt and water cannot. A mixture of sand and water is a suspension, and a mixture of salt and water is a solution. The particles in the sand mixture are much larger than the ions in the salt mixture. Sodium chloride ions. The sand particles are too large to pass through the filtered paper, the ions are not. This is another example. So now we know suspension and solution. Now another type of liquid is coming, that is colloid. What distinguishes a colloid from a suspension and a solution? A colloid is a heterogeneous. This is also like suspension. It is a heterogeneous. It is the particles in the solvent, the solute particles in the solvent will never dissolve water uniformly with a uniform density. A colloid is, see why I am telling this Tyndall effect is, all these things I am telling you like a chemistry for Tyndall effect only. I have to tell you what is Tyndall effect, which is applied for the propagation of light through optical fiber. For that, all these things I am telling you. Basic thing. A colloid is a heterogeneous mixture containing particles that range in size from 1 to 1 to what? 1 nanometer to 1000 nanometer. 1 nanometer to 1000 nanometer. A colloid is a heterogeneous mixture containing particles that range in size from 1 nanometer to 1000 nanometer. Colloids have particles smaller than those in suspension and larger than those in solution. See, a colloid is a heterogeneous mixture. It is similar to that of suspension. It is a heterogeneous, but the particle size, when you compare to the colloid, suspension, in the colloid, the particle size is of range from 1 nanometer to 1000 nanometer. 1 nanometer to, it is in between, that is a colloid, the particle size is in between solution and the suspension. Colloids have particles smaller than those in suspension and larger than those in solutions. These intermediate sized particles cannot be retained by filter paper as are large particles of a suspension. So they do not settle out with time. The particles are spread or dispersed throughout the dispersion medium, which can be solid, liquid, or gas. Such colloidal particle is present in the what? In the atmosphere. Because of such colloidal medium is responsible for the scattering of light when when a light passes through it. As a result, the path of the light is visible. That is the Tyndall effect. So we need a colloidal medium. So the when a light passes through the glass fiber, how the path of the light is visible? Then means the glass fiber is made up of solid. The particles in the glass fiber is such that when a light passes through it, it will scatter the light. So the path of light passing through the glass fiber is visible by the principle of Tyndall effect. Apart from that, this Tyndall have told about the total internal reflection. 3 cases when a light passes through the denser to rarer medium. That we will see in detail. Now, so this is the basic thing for Tyndall effect. This when a light passes through the colloidal medium, the particle size or any medium, when the particle size is of reasonable size, of reasonable range, the light, when it passes through that medium, it is scattered by the particles and the path of the light is visible. This is called Tyndall effect. So the Tyndall effect, we will see again. So the dispersed medium may be in a solid form or a liquid form or a gaseous form. So you cannot see a beam of sunlight unless light passes through the particles of water or dust in the air. These particles scatter the sunlight. Similarly, a beam of light is visible as it passes through a colloid. The scattering of visible light by colloidal particles is called the Tyndall effect. This This is the basic principle for the when a light passes through the optical fiber. When you are viewing the propagation of light, visible, when the light is visible, when it passes through the glass needle, or when it passes through a liquid, when the path of the light is visible, this is due to the scattering of the visible light by the colloidal particles in that medium. This is called Tyndall effect. See, in this diagram, light is allowed to pass through the solution, colloid, and suspension. See, the solution, the particle size is very, very small, of 1 nanometer range. So, it cannot able to scatter the light. So, the light passing through the solution is not seen. Even though the light is passing through the solution, it is not visible. But in the colloid, the particle size is between 1 nanometer, like that of it is greater than 1 nanometer compared to the solution, and less than 1000 nanometer compared to the suspension. So that particles in the colloid will scatter the light, and the path of the light wave through the colloidal solution is clearly visible. In the suspension, the particle size is larger, so even though it is scattering the light, the clarity is not that much. It is scattering too much. That is the thing we can see here. So this is by the principle of Tyndall effect. Suspensions also exhibit Tyndall effect, but the particles in solutions are too small to scatter the light. So the Tyndall effect, to explain Tyndall effect, colloidal particle is good. See, again, I am after explaining the Tyndall effect, I am giving the same picture, showing the same picture. The atmosphere contains particles of water and dust. It is compared to the colloidal particles. How the particles are distributed in a colloid, like that. The atmosphere contains particles of water and dust dispersed throughout it. As the sunlight passes through it, the particles it is scattered. However, not all wavelengths are scattered to the same extent. Red light is of maximum wavelength get scattered more. A misty or a foggy evening would be ideal for seeing a red sunset. There would be a large number of particles to scatter the sunlight. Because of that only you can see a red sunset. Only in the misty and foggy evening, because particles are there to scatter the light. Now, light scattering phenomena in Tyndall effect. Sky looks blue. What is the reason? Sun allows all the wavelength to pass through it. But blue light has a maximum scattering in sky, because blue light have a shorter wavelength, so it make a maximum scattering in Ashman, means sky. So only color visible in sky is blue. Sun looks red. Sky looks blue because it scatter the what in the sky, the particles scatter the what shorter wavelength, that is in VIBGR, violet, indigo, blue, green, yellow, orange, red. Blue is of shorter wavelength, 4,000 Armstrong unit, 4,360 Armstrong unit, around that. That is the blue color. So Armstrong unit means 10 power minus 10 meter. Nanometer means 10 power minus 9 meter. So blue light is of order of 420 nanometer, means it is having a shorter wavelength and it has a maximum scattering in the sky. So sky appears blue. That is due to the Tyndall effect. Why sun looks red means sun through all wavelength light. Why it looks red? All wavelength of light is there, but how it looks red? Red light make minimum scattering. So because the wavelength of the red is larger, 6,000 VIBGR, it is a larger wavelength range. So scattering is minimum scattering. So red color directly reach to earth due to the minimum scattering of larger wavelength of the light. So Prithvi means earth. From the earth, sun looks red. All are due to Tyndall effect. Now, this John Tyndall's effect about scattering of light. How it is, again, this John Tyndall, this after explaining this Tyndall effect, he take a filled a water tank he constructed a water tank, a bending water tank, a bend-shaped water tank, and allow the light wave to pass through. I will show you the video in next class. Allow the light to pass through the water tank. The light will reach the bend water tank. Through the bend water tank, at one end a light is allowed to pass through, and even that water tank is bend. That water tube is bent at glass tube. It is the light is coming at the exit end by the principle of total internal reflection. This is demonstrated by the John Tyndal. That principle is used in fiber optic communication. That we are going to see in next class, because already the time is over. I think I will tell you how this Tyndall effect is used in total internal reflection, for which is the basic principle for the propagation of light through optical fiber in next class. See, a light is allowed to pass through it, and by the principle of total internal reflection, within the glass tube filled with water, the light is reaching the exit end. Like this, on demonstration through the this is actually with the optical fiber. Like this, a bend tube is constructed, glass tube is constructed, filled with water, and light is allowed to come to one end, and it is reaching the exit end. And by the principle of total internal reflection, it is reaching the exit end by means of John Tyndall effect. That I will explain in next class. Okay, next basic principle I will explain in next class. Now it is the time, I think. Shall we take the attendance?
Yes,
I think everybody is there. What?
Yes, ma'am.
Yes, 49. Very good. See,
Yes, ma'am.
students, it is for your benefit only. Okay, please attend the class. There is a some students in some other branches, they didn't have an awareness that there is an online class, and it make a then all are called and warned. So please attend. This is for your. It is a refreshing. It is a extra class for you. So please attend and use this. Enjoy this benefit, because again these classes will be taken with the counseling students also. So it is not going to end, but it is an extra class. It is a benefit given to you, so utilize it. Don't get absent to any class. Okay, don't get any. But regarding computer science, you are all excellent, very good students. I get a very good feedback about you. So please attend all the classes. If you have any trouble, you are having a contact number, immediately you tell that you are not able to attend the class, and join the class. Okay, so don't miss any classes. You attend the classes till anyway. Soon it will become a offline class. Let we pray for it. Okay, so that we can enjoy a very nice class in the classroom soon. Okay, Pa, I have seen all the attendance present, so no need to give attendance today. I have checked all these things, so you can. Why 48? Somebody have left right now. Anyone absent? Okay, you tell me the attendance and leave. 49, I have seen, I think. Mohammed Yazir?
Present, ma'am.
Mohan Kumar? Yes. Mohan Kumar? Mohan Kumar? Yes, Mohan Kumar. Mugil?
Present, ma'am.
Muralidharan?
Present, ma'am.
Once you give the attendance, you can leave. Okay. Mohan Kumar is not there. Rahul KS?
No, present, ma'am.
Very good. Navaneet?
Present, ma'am.
Once you give the attendance, you can leave. Nisant?
Present, ma'am.
Pavitra? K. Pavitra? Pavitra? You are not attending the class. Just doing just to switch on, join and went for somewhere to do some of your personal work. I think. Pavitra. Pavitra K is there, but she is not attending, answering the attendance. Huh? Yes, you are audible. Okay, Pavitra. Nishant.
Present, ma'am.
Purna Sendur.
Present, ma'am.
Prakash.
Present, ma'am.
Prakatesh. 58. Prakadesh. 58. He is there. But he is not, he is doing his own job, I think. Rahul B.
Present, ma'am.
58, present, ma'am.
Okay. Rahul V. Raghuram.
Present, ma'am.
Present, ma'am.
Two Rahul V and Rahul V. Both spelling is different. 59 and 61. Next, Rakesh.
Present, ma'am.
Ramanathan.
Present, ma'am.
Manish Raja.
Present, ma'am.
Rohit Kumar. Rohit Kumar R. Rohit Kumar R. He is not there. Rohit Kumar. Rohit Kumar. Sadanand.
Present, ma'am.
You always, now you are attending with your ID. Sadasivam.
Present, ma'am.
Sahitya.
Present, ma'am.
Saktivel.
Present, ma'am.
Samvardhana.
Present, ma'am.
Sanjit.
Present, ma'am.
Sanjay B.
Present, ma'am.
Sanjeev A.
Present, ma'am.
Sanjeev B.
Present, ma'am.
Sandosh A.
Present, ma'am.
Sandosh Kumar S.
Present, ma'am.
Saran and Sarat.
Saran, present, ma'am.
Sarat. Sarat.
Present, ma'am.
Both are attending in a same phone. Sibiraj.
No, ma'am.
Present, ma'am.
It's okay. Anyway, you have to attend. Sibiraj.
Present, ma'am.
Okay, pa. Siddharth.
Present, ma'am.
Sivasankar.
Present, ma'am.
Sri Harish.
Present, ma'am.
Subhash.
Present, ma'am.
Sugan.
Present, ma'am.
Suganeshwaran.
Present, ma'am.
Sujishri.
Present, ma'am.
Suman.
Present, ma'am.
Suvita.
Present, ma'am.
Tambiraj. Yuva Rubini.
Present, ma'am.
Vaibhav.
Present, ma'am.